Hey, we're here at Supercomputing 22. I'm on the AWS booth. There's been a ton of activity. I'm here today talking with Steve Litster.
So I manage the healthcare life science compute specialist team. So this is a collection of high performance computing, containers, hybrid and flexible computing. And we try to build line of business solutions to accelerate scientific insights. So that's our driver. But probably going back to like 10, 15 years ago, a lot of clusters we were building in life sciences were homogeneous. They were running primarily in silico workloads. What we've seen over the last 10 years is a shift. Now we're going from high performance computing, now high throughput computing as well. Sequencing, imaging, now we're layering on AI ML workloads. So those homogeneous environments have really become heterogeneous. It's fairly typical to have like 300 to 400 applications in a life science HPC environment. So you actually build your cluster to the maximum spec. So typically when you buy a cluster for life sciences, you've got the work nodes, which are typically 8 to 16 gigs of RAM per core. So you buy for the largest jobs, which tends to genomics.
Yeah.
Every node has InfiniBand.
Yeah. And just in case you need it.
Just in case. Yeah. And then you buy in high memory nodes and GPU nodes as well. And what's really interesting, when you actually start to do an analysis of the logs of what's actually being used, you'll find that the average runtime, like 98% of jobs finishing under about 4 hours.
Yep.
Less than 7% of jobs actually use MPI, even though you've enabled every node to run MPI.
Less than 7% of the jobs.
Because many of those fine-grained MPI jobs that you used to scale out are now on GPUs.
Yeah, right.
So, but you still buy in an entire cluster with InfiniBand or low latency interconnects to 7% of the jobs.
Yeah, okay.
So what we really focused on is building these fit-for-purpose architectures. Because the genomics workload is going to run on something very different than, say, a cryo-EM workload or a computational chemistry workload.
Right.
So what we've been doing is analyzing those logs. Many of the customers we work with bought systems about 5 years ago, which coincided with the latest Skylake, the latest GPU, the latest SSDs for storage.
Yeah.
And now we're looking at, do we refresh or do we move to cloud?
Right.
And we're comparing clusters of 10, 15,000 cores, whereas today with the new chipsets, you can maybe get away with
5,000 cores.
Easily. And I think that's even pushing it. Definitely 1 to 2 or 1 to 4 performance improvement. Again, when you look at the analysis of the logs, really most systems are at 50%, 70% utilized.
Yep.
So what we've been doing in the design for purpose or fit for purpose is saying, okay, maybe you do 60% reserved instances, 20% on demand, 20% spot. So we model different scenarios.
And so on the spot stuff, you would just run all of the short workloads.
Exactly.
So you don't care if it gets interrupted by spot. You just run it again, right? And you haven't lost much time. So you just segment down into those different procurement types. And now you're doing CPU and architecture optimization, but you're also doing procurement optimization in a way.
When we we used to buy the clusters, 8 gig to 16 gigs per RAM per core. Again, about 90% of the jobs use less than 1 gig of RAM per core. So we've got
90% are using less than 1 gig of RAM per core.
Exactly. In terms of volume of jobs.
Yeah, and RAM is not cheap.
Nope.
It is not cheap. It's a huge factor in the actual architecture of the box.
Yeah. So now with instances, we can mix and match.
Yeah.
And if you've got these very fast running jobs in terms of less than a second that use megabytes or even kilobytes of RAM, we can actually just spread these out over ginormous, very diverse set of instance types.
And so how's this message getting received when you talk to the pharma companies about this?
And I'd say we've really seen a shift in the last couple of years with COVID as well. So there's a few changes there. Right. One, increased collaboration, commercial sector, public sector, and academia.
And that was driven by COVID. Okay,
that was driven by COVID, so they had to work there. But then they're deploying the same model, so you want this portable architecture so they can run in a consistent manner. And really looking as well to drive down costs. So how do we start to build these collaborative platforms but keep the costs well contained? And this is why we're building those fit-for-purpose architectures.
Right.
Which really is to reduce the cost and, if anything, enable the science. So the narrative is moving away from total cost of ownership, but how we can enable science. can we do more jobs for less? Can we increase the throughput?
So you were one of the folks working with Moderna during the pandemic,
Yes.
right? And
Yeah.
I can't think of a better example of put powerful tools in the hands of people that need them and give them immediate access to it whenever they need it.
Yep.
I can't think of a better example of how that can be impactful for science.
And the thing is,
Right.
it's 42 days from like sequencing
To a candidate drug.
yeah, and that's just mind blowing. And it's completely changed the industry. This is what's changing the life science industry.
Are you now seeing that roll out into the, like, are you seeing that basic change in behavior rolling through the rest
Yes.
of that space?
So that's when we're engaging with the customers now, and we're speaking more and more to the line of business. So we're developing these use cases. So we speak to the line of business and how we can accelerate their workloads.
Right.
That's really key. It's if you had this, what could you do with it? Rather than, I've been waiting for my job to execute for the last 2 days. Now they can instantly access that. And it can scale, they can small, they can go large. And it really is impacting the science to
Yeah.
accelerate the science.
I've got my favorite t-shirt says that it takes decades to create a new scientist, to grow a new scientist. We have to make them all as productive as we possibly
Absolutely.
can.
Yeah.
Right? So, eliminating all those queues and waits and just, I don't know, access to resources and stuff, that's going to move the science, right?
Yeah. That's it, it's accelerating science. Even with things like cryo-electron microscopy, typically people have been running this on desktops and it would take a few weeks to analyze. We can actually do this analysis in a couple of hours now, or 2 to 4 hours.
Are you seeing this changing the conversations you're having with CIOs at these places? Are they focusing on research scientist productivity as a measure of
Absolutely.
what their impact is in the organization?
Yeah, because the speed of science is advancing so quickly. The techniques, the amount of data being produced off these instruments,
Right.
you need to be able to process it in near real time. So it's not just the cost of the infrastructure, it's the cost of the FTEs and the scientists and the IT staff who need to be getting on with that research.
Right. There's no point having a scientist who took 20 years to educate,
Yes.
PhD and all of the skills that they needed to have as that came after that, sitting around waiting for an analysis to arrive or data to come out of a machine. You need that's dead time that's horribly expensive.
And it's becoming more and more difficult to find these new drug candidates. So, the low-hanging fruit, the small molecule blockbusters are very difficult to find out. So now you've got much more advanced techniques needed as we start moving into biologics. So you're now doing like multimodal analysis.
Yep.
I'm combining genomics with imaging, with chemical assay data, with structural data. And the focus is becoming less and less on things like TCO and its enablement of science. How can we drive this pipeline?
And you're hearing CIOs talk about the cost of the FTEs in the science groups as a factor in their decision making.
Exactly.
Mind blowing.
It's completely changing. Exactly. And it's maybe not a lot of people know this, but typically a drug development cycle or life cycle from research all the way to clinical release is 12 to 15 years for one drug, and a cost of $2.5 to $5 billion.
Wow.
Like that has to come down. We have to get those treatments out faster.
What? And to state the obvious, if we waited 10 to 15 years for the COVID vaccines, you and I wouldn't be standing here having this conversation.
And that's
we
what's
would be
really changed it.
Yeah.
And I honestly believe that the power of cloud, enabling collaboration, increasing the throughput, massive scale analysis and throughput from genomics, imaging data, that helps generate these therapies, accelerate scientific insights, and that's where we are today.
If you learned something from this talk, then please consider giving us a like and subscribing to the channel so you can find out when more videos like this are available. And if there's an area you'd like to see us go deeper into, don't hesitate to reach out and let us know. See you next time.